So one important kind of free body diagram that's important to set up is one's about banked roads. So this has to do with the idea that if you are attempting to drive or make a turn, like on a circular path, like if you're going pretty slow, it's easy to make a circular turn. Like if I'm driving in a car here, and this is an aerial view of my car, and I want to make a right turn like this, okay, I'm gonna do this circular path. But what force is gonna act as my centripetal force would be friction with the road. So I don't know if you've ever tried to, if you're in a car and you try to take a turn way too fast, you're gonna skid because the friction, you're not gonna have enough friction to make that turn. Like it's not gonna provide enough centripetal force to allow you to make that centripetal acceleration. But a common thing you can do on racetracks when you're trying to go really, really fast and move really fast on a turn, same with highway entrances or exits, or highways that are making big turns, is you bank the road, okay, so that you're at an angle. And what this, and let's just describe what's happening here. So like on a racetrack or on a freeway, you might have a turn where the car is at an incline here instead of being flat on the ground. And let's draw a free body diagram of the car here. So you see like it's moving in a circular path at this angle. Let's assume for simplicity that it's the same angle all around the path. If I were to draw a free body diagram, I would say, well, I have gravity coming down. I have a normal force perpendicular to the incline, right? And then I'm going to ignore friction. So let's say there's no friction. So we're banking it assuming no friction. These are the only two forces that we have here. So you can see that you can make this turn without friction, even if you are on ice, because the net force will be this way. As long as you're going in the circle properly, your acceleration is going to be in this direction towards the center of the circle. That's my centripetal acceleration because I'm going in a circle. So the net force is going to cancel out. So if I were to split this normal force into its vertical and horizontal directions, note that normally in an inclined plane, we always do the direction like along the ramp as the x-axis. But here it's better to leave it as horizontal because the acceleration is horizontal. The acceleration is not up or down the incline. The acceleration is horizontal. So in this case, it's better to leave your x and y coordinate systems as positive x to the left here and positive y up. So really, it's the normal force that has the different components. See how different this is with the inclined planes? So it's an inclined plane, but we do it horizontally and vertically as opposed to rotating it like we were doing just when it's sliding up and down the inclined plane. And that's because the acceleration, see, if I do it in the coordinate axes where I go down the inclined plane and up, my acceleration has both components in the x and y direction, and it's just more tedious to calculate it that way. So here, what are my forces, or what are my component forces? This force here is Fn. The horizontal component is going to be Fn sine theta, and the horizontal component, or the vertical component, is going to be Fn cosine theta, because this angle is theta, so the adjacent side is cosine, the opposite side is sine. Okay, and so there's no acceleration in the vertical direction, right? Because the acceleration is all horizontal. So in the y direction, we'll find that mg is equal to Fn cosine theta. And in the x direction, the net force is just Fn sine theta. But the acceleration is centripetal, so it's equal to mv squared over r, where r is, we'll use little r. V is the speed that you're going, and R is that. So it just depends on the context of the problem as to what you're trying to solve for. But this is the general. Like you can calculate that. Maybe if you're trying to find the ideal, sometimes you're trying to find the ideal banking angle for a certain maximum speed. So if I'm trying to solve for theta, I'm going to divide these two equations to cancel out the normal force. So I'm going to say Fn sine theta over Fn cosine theta is equal to, say, mv squared over r divided by mg. And we did this before, kind of, but this is tangent of theta is equal to v squared over rg. And so your ideal banking angle is going to be the inverse tangent or arctangent of v squared over rg, like that. Okay, so that's ideal banking angle. I don't want you to memorize this equation. I just want to make sure you understand how to set up the free body diagram and draw it for something with a banked incline. Now, if I were to add friction, friction's going to make it kind of more of a complicated. So let me repeat the exercise. But I have this angle, and my car's right here. So I have my force downward. I have my normal force. Now, the key part is which direction is friction going to help you? Now, if you are, friction is supposed to help you stay going in the circle. So the frictional force is actually going to be this way. Because if you don't have enough friction, you would actually be trying to slide up the ramp. So the friction's probably going to help you go down this way. It kind of depends on the scenario, but if you're trying to go your maximum speed around the ramp, you want friction to assist you with that turn. So that means it's going to go down inside the ramp. Now again, because the net acceleration is horizontal, we still have to project all these. Like this one is still the same. That's angle theta. But I have to, the frictional force will only have a portion in the horizontal direction that I care about. Like there. It's going to have a vertical direction and a horizontal direction component, right? And this angle here will also be theta. Okay. And so if I look at the x and the y directions, then in the horizontal, in the vertical direction first, I have Fn sine theta, cosine theta, would have to equal mg plus, my Fn cosine theta would have to equal mg plus this portion of the vertical, which would be force of friction sine theta. And force of friction sine theta, by the way, the force of friction is mu times the normal force. Well, it can be. It may or may not be. Because what kind of friction is this? If we're not sliding up and down the ramp, this is static friction that's helping me. So this would be static friction. Okay. Anyway, so that would be the setup, and then the x direction, you would have not only the normal force, you would have the normal force, which would be Fn sine theta, like we did before, but you would have a little bit of friction, which would be force of friction cosine theta. And that equals mv squared over r. Okay. So that's kind of the idea. What would friction do? But you have to be a little more careful, and you don't do the big part. I wanted to talk about the banking was that really you're not going to do your x and y up and down the ramp like we do, like when you're sliding up and down the ramp. When you're moving in a banked and you're doing a circle, because the acceleration is all horizontal, you want to do just horizontal normal up down for the y direction and left right for the x direction. So let's take a look at some of these examples for these banking problems. So problem 1, what is the ideal banking angle for a gentle turn of 1,200 meter radius on a highway with a 29.2 meters per second speed limit, assuming everyone travels at the limit? Okay, so we're going to take a look at our free body diagram, right? So we got a car here on an incline. The radius is 1,200 meters. Oops, no, I said 1,200 meters. The speed of the car is 29.2 meters per second. There's no ideal banking angle, means no friction. No friction's involved, right? So we're doing free body diagram is gravity and a normal force perpendicular to the plane. But remember, we want to split this up is the centripetal acceleration is to the left like this, right? So I want to decompose the vectors. I don't want to decompose mg. I want to decompose them horizontal and vertical, not up and down the ramp. So if this is theta, this side is Fn sine theta, and this side is Fn cosine. The opposite side. So this is Fn over here. The opposite side is Fn sine theta over here, and then this side is Fn cosine theta. Right? And so in the vertical direction, there's no acceleration up and down, right? It's sitting there. The only acceleration is towards the center of the circle. That means in the y direction, the vertical forces cancel, right? Fn cosine theta equals mg. And in the x direction, applying net force equals ma. There's only one force in the x direction. It's Fn sine theta. And what is its acceleration? It's m times the acceleration. The acceleration is centripetal acceleration, v squared over r. Right? And so I want to figure out what theta is. And I know that this is, I can solve for Fn here. It's mg over cosine theta. And I can plug that into there. So I get mg over cosine theta times sine theta equals m v squared over r. The m's cancel, divide by both sides. Sine over cosine is tangent theta equals v squared over r. So tangent of theta is then v squared over rg. And so theta is the inverse tangent of v squared over rg, right? So that's inverse tangent. What is the speed? Well, the v is 29.2. The r is 1200, and g we'll just say is 10, right? So it's going to be inverse tangent, 29.2 squared divided by 12,000. So I get about 4 degrees, okay? Very slight angle if the radius is that big. Okay, let's do a similar one here. Let's do another example. What is radius of bobsled turn banked at 75 degrees, taken at 30 meters per second, assuming it's ideally banked? So here's what is the radius. We can kind of still do, it's the same picture, right? I like you guys to know, and I don't want you to memorize equations, right? I want you to understand the process, right? But you can use, we already just did this one, so you can redraw the free body diagram, things like that. What you should get in the x direction, right, is that Fn, just like we did before, Fn sine theta should equal mv squared over r, and in the y direction you should get Fn cosine theta is equal to mg. All right, that's what you should get, because in the y direction the acceleration, right, is 0, and yeah. So kind of rearranging, right? Fn is equal to mg over cosine theta. Plugging that into there, you're going to get mg over cosine theta. It's the exact same process we just did. M's cancel. And if you rearrange that, you should get tangent of theta is equal to v squared over rg. Now, what do we want to solve for? In this case, I want to find the radius. So I'm actually trying to solve for r. So r would be v squared over g tangent theta. If you just rearrange this equation for r, multiply by r to bring it up, divide by tangent theta over there. So this is 30 squared over g, which is 10, and then tangent of 30 degrees. I get 900 divided by 10, divided by tangent of 30. I get 155.9 meters. Okay? Now, what was the centripetal acceleration? Well, that one was v squared over r. Now that I know the radius, I can figure out the centripetal acceleration. Right? So 30 squared divided by that number is about 5.8 meters per second squared. All right? Let's look at this third example. Here's one we're going to involve some friction. So a car takes a bank curve at less than ideal speed. Friction is needed to keep it from sliding towards the inside of the curve, a problem I see mountain roads. Calculate the ideal speed. Ideal speed is no friction, right? So we're going to just use the relationship that we had solved before in the previous two problems, right? Tangent theta is v squared over rg. I don't recommend you memorize this equation. I just remember how you're going to do that, but that's how we deal with ideal. So the ideal speed is really the square root of rg tangent of theta. So that square root of the radius is 100 times 10 times tangent of 15 degrees. But go through that process, right? Draw the free body diagram. I get here 16.4 meters per second. So now, what is the minimum coefficient of friction needed for a frightened driver to take the same curve at 5 meters per second? So now what's happening is you're going slower, right? So in this case, what's happening is we're going slower than that speed. Okay, so we need less centripetal acceleration. So if I draw the free body diagram of this guy, let me just put it as a dot over here just to make it a little clearer. I'm going to have gravity going down on this car. I'm going to have normal force. And here's where you have to think about what's going to happen. Well, if there's no friction and he weren't moving or he's moving too slow, he's going to slide down the ramp, basically. He's just going to slide down the ramp. So what happens is friction is reducing his force in the centripetal direction. And by reducing it, that's how it's matching the reduced centripetal acceleration. See, we need less centripetal acceleration. And so that means we need less force in this direction, right? The direction of the centripetal acceleration is still to the left, just as a slower speed. Okay, so that's kind of important to kind of recognize the friction would have to be going upward when the car is going too slow. Now we decompose the forces, both horizontal and vertical direction, right? Oh, and the angle of this is still 15 degrees, right? So we want to decompose horizontal and vertical components. So the Fn still does that same thing here. This is Fn cosine theta. And this here is Fn sine theta. But the frictional forces also has to be decomposed. This is force of friction sine theta. This is force of friction cosine theta. Right, because these angles here are theta. Okay? So that's the decomposition into the components. Now we're going to do the x direction, and we'll say this direction is positive. In the x direction, net force equals ma, which Fn sine theta is horizontal, but F cosine theta is going the other direction, in the rightward direction, Ff cosine theta, and that's equal to mv squared over r, right? Because this is centripetal acceleration in the x direction. How about the y components of the forces? Well, the upward force, there's no vertical acceleration. The car is not going up and down like that, or it has any vertical component of acceleration. So therefore, the upward forces, which I have Fn cosine theta and Ff sine theta, have to equal the downward forces, which is mg. Okay? So this is kind of the relationship that I kind of have here. And my goal is to relate the force of friction and the normal force by this quantity. We need force of friction to be less than or equal to mu Fn. Okay? So how are we going to solve this kind of setup here? Well, let's plug in some numbers, because we do have some numbers here. So this is Fn cosine 15 degrees plus force of friction sine of 15 degrees. And that's equal to m, or 10m, I guess. 10m. We don't have the mass of the car, but hopefully that won't matter. And here we have Fn sine 15 degrees minus force of friction cosine of 15 degrees equals mv squared, that's 5 squared, and then the r, what did they say the r was? 100 meters. Okay, and that's 25 over 100, that's 1/4 m. Okay? So I want to ultimately solve this systems of equations. I want to find force of friction in terms of Fn or something like that, right? So it's a little tricky on this one. You could try to like isolate one variable and then plug it in. It gets pretty messy though, but that's the basically, because the two unknowns are really force of friction and the normal force, right? So yeah, I'm going to attempt to do, I'm going to divide both of these by sine of 15 degrees and divide this guy by cosine of 15 degrees, okay, to get the Fn by itself. So this would be Fn minus force of friction cosine of 15 degrees over sine of 15 degrees equals m over 4 sine of 15 degrees. And then this guy, I'm going to say Fn plus force of friction sine 15 degrees over cosine 15 degrees equals 10m. Okay. And then I want to like kind of subtract these two equations, right? So I'm going to put this equation, or I'm going to put this equation right underneath it and then subtract them. Okay, so I'm going to subtract these so the normal forces go away, and then the force of friction will just be the sum of these two, because I'll do this plus this. So it'll be F sine 15 degrees over cosine 15 degrees plus FF cosine 15 degrees over sine of 15 degrees. And that's equal to this thing, 10m minus m over 4 sine 15 degrees. Okay, so let's go ahead and put some numbers in here. This is 0.268 force of friction plus this one is 3.732 force of friction equals 10 minus 1 divided by 4 divided by sine of 15 degrees is a 9.03 m. Okay? So just combining these two numbers, these two force of frictions, oops. These two added together is 4 times the force of friction is equal to 9.03 m. Okay? So here we've solved for one part. Force of friction is, let's do that 9.03 and divide it by 4. To solve for the force of friction is 2.26 m. Okay, and then you can just solve for the normal force for one of these. Like, for example, this guy would tell us that the normal force is equal to 10m minus force of friction times, I just write as tangent of 15 degrees. Sine of 15 over cosine of 15 is 15 degrees. So that's 10m minus 2.26m times tangent of 15 degrees. There. Okay, and then we just combine those together. 10 minus that times tangent of 15 is 9.394 m. Okay. So plugging into here, plug into our original equation, force of friction less than or equal to mu Fn. That means the force of friction, which is 2.26 m. And m is the mass of the object, right? It's not meters. Mu times 9.394 m. The m's cancel. And I could say mu is greater than, I can just divide by this 9.394. And I get 0.24. So mu has to be bigger than 0.24 to make that turn at that speed. You can see the static friction is a lot more complicated in that scenario, in that inequality. Now, you could shortcut it and just say, set these two equal to each other. That would have been okay. Okay, and that would have been fine to solve it. I prefer the not equal to sign, but if you wanted to save yourself a trouble, you can set it equal to. Just remember that it's a minimum. So what they're asking for you to do is figure out like when would the static friction be at the maximum value. Okay.